Bismillahirrahmanirrahim. Assalamualaikum warahmatullah. Hi students, welcome to my lecture on pharmacokinetic parameters and concepts. This is the second lecture in the pharmacokinetic series. If you haven't done so, please look at my first lecture where I talked about drug disposition processes. For the purpose of this lecture today, I'd like to introduce you to the time versus plasma concentration curve. So if we plot plasma concentration, which is the level of the drug in the plasma, and plot it against time, we will get something like this, which is the absorption phase of the drug, followed by the distribution and metabolism phase, and finally the metabolism and excretion phase of an orally administered drug. As you can probably still recall from the first lecture on the pharmacokinetic series, there are four components of pharmacokinetics, which are absorption, distribution, metabolism, and excretion. All these four concepts do not exist exclusively. They are constantly interacting with each other, and the components distribute towards the concepts that we are going to discuss about today. Let's go back to the plasma concentration versus time curve. In the first part of the curve, the increase in plasma concentration here is contributed by the process of absorption of the drug from the GI tract. Of course, majority of the data contributing towards the increase here is due to absorption, but at the same time, as the drug is being absorbed into the systemic circulation, the processes of distribution and metabolism has already started, and that is evident when you see as the plasma concentration is reaching the maximum there. It's actually blunting out or rounding out before it reaches the maximum plasma concentration. In the second part, in green here, most of the drop in plasma concentration is due to the distribution and metabolic processes that is happening on the drug. So during this part, the drugs are being distributed into tissues, into the liver, into the brain. Those that reaches the liver will undergo metabolism as well as some degree of excretion. At the same time, those that reaches the kidney will undoubtedly be excreted quicker compared to those that has been distributed to other tissues. Finally, the third part of the curve is mostly down to the metabolism and excretion. As the drug is being metabolized and excreted, the free drug that was distributed into tissues just now will re-enter the circulation and again be submitted to the processes of metabolism and excretion, and this process continues until the drug is completely eliminated from the body. In the absorption phase, one parameter is important here, but before that, let's compare the plasma concentration versus time curve of an intravenously administered drug compared to an orally administered drug. So the intravenously administered drug will have a curve similar to this one in red, where at time 0 the plasma concentration is at maximum, because if you recall from our previous video, intravenously administered drug does not need to undergo any absorptive processes from the GI tract, so they will enter the systemic circulation directly, and over time will constantly be exposed or um, constantly undergo processes of metabolism and excretion. Compare that to the orally administered drug that we've seen a few times before. There is an absorptive phase before the drug is metabolized and excreted as per the intravenously administered drug. Now, if you see here, the areas under the curve for both the orally administered as well as intravenously administered drug can be calculated, and both of these values contributes toward the calculation of bioavailability. And bioavailability of an orally administered drug, the formula is as shown here, and most of the time it will not be 100%. Let's look back at this plasma concentration versus time curve of an orally administered drug, and if you can see here, distribution plays an important role, not just in the initial part, but mostly in the second part of the curve, where the distribution determines how much of the drug is being distributed into the tissue away from the systemic vasculature. Consider a situation where a drug is given intravenously to a patient who has roughly about 5 liters of blood at a dose of 100 milligrams. Therefore, the concentration of the drug in the patient's blood should be around 20 milligrams per liter. So, just so that you are reminded of how the plasma concentration versus time curve for an intravenously administered drug is. If at the initial part the concentration is found to be only 15 milligrams per liter, assuming that of course the rate of metabolism and excretion is 0 at this point, where is the other 5 milligrams per liter? So the answer is to that is that it's probably in the tissues away from the systemic circulation. Why this happens is that when we take drug concentration levels and send them to the lab, we are actually just measuring the level of the drug in the systemic circulation, not accounting the fact that as the drug enters the systemic circulation, be it if the drug is given intravenously or even orally, it is straight away redistributed to either fat or kidney, liver, and other tissues. So, if we were to consider the multiple other compartments, and if we are able to sample and measure drug levels from the other tissues, the sum of all these levels would probably show the total amount of the drug in the body. Going back to this patient, concentration is given as a formula as shown here, which is dose over blood volume. In practice, we know how much drug that we give, or we can control how much drug that we give via the dose, and after a period of time has lapsed, we can measure the concentration of the drug by taking a sample of the patient's blood. In that sense, we can determine the volume of blood and probably other tissues in which the drug is distributed by modifying the formula here a bit. This volume of blood in which the drug is distributed is the one known as volume of distribution. So that's a straightforward definition of volume of distribution. What is the importance or significance of knowing volume of distribution of a drug? VD is a measure of how hydrophilic or lipophilic a drug is. A very hydrophilic drug means that it will stay confined in the vascular compartment. It will have a small VD, roughly of about 5 liters, because that is the volume of your blood. Whereas a very lipophilic drug, a drug that literally hates water, will redistribute into the tissue more readily, therefore will have a apparently large VD because it is contained in a much larger volume. More importantly, VD is a measure of tissue penetration. A drug that has a high tissue penetration means that it can go deep into tissues, even those tissues that are not very well vascularized would probably have a very large VD. So consider a situation where a drug is needed to treat an infection in the liver tissue. Okay, does it need to have a small or large VD? Taking into account that the liver tissue is not well vascularized. Okay, now we come back to this graph again. The reason that I keep showing this graph is just to familiarize yourself with all the various stages in the plasma concentration versus time curve. We've talked about the absorption and slightly about the distribution. Now I'd like to start talking about the process of excretion. For the body, the process of excretion will eliminate a constant proportion of a drug from the body, and this is referred to as first order kinetics of elimination. Is there any other? Definitely. Okay, so again, drug excretion kinetics, there are two of them, first order and zero order. For first order, a constant proportion of drug is excreted per unit time. So for example, 10% of the original concentration is excreted per unit time. And why this happens is that the processes involved, the metabolism and the excretion mechanisms, they are not saturated by the drug. Okay, I'll explain to you what this means when I talk about zero order, in which there is a constant amount of drug excreted per unit time. And the reason for this is that in zero order kinetics, or rather drug that follow zero order kinetics, its metabolism and excretion mechanisms can be saturated. Take for example a drug that needs extensive liver metabolism for it to be excreted from the body. Now, as we know, the enzymes in the liver responsible to metabolize drugs for excretion is limited in number. So because of this, the concentration of the drug does does not play a role in the rate of excretion of the drug. Rather, the amount of enzymes in the liver plays the most important role. And for that reason, that is the reason why we say that the process of metabolism or the mechanism of metabolism can become saturated. For first order kinetics, almost all drugs given at its determined therapeutic concentration will follow this first order kinetics. So as you increase the concentration of the drug, the rate of excretion increases. However, for zero order kinetics, except for some exceptions, some drugs, even given at a therapeutic concentration, will still follow zero order kinetics, but as a general rule, zero order kinetics will be followed by all drugs if the therapeutic concentration that is if the drug is given at a concentration that is very high, to the point that even most processes of metabolism and excretion is saturated. Now let's come back to this graph. If you can see here, at the level of max plasma concentration to the level of 50% plasma concentration from max, the graph or the curve drops in a linear fashion. Okay, this is the point where the rate of distribution and rate of excretion is at maximum. From 100% to 50% plasma concentration, the time that is taken for the plasma concentration to drop is called the half-life. The half-life of a drug, the half-life of a drug is related or associated with volume distribution, in the sense that the higher the volume distribution, the longer the half-life would be. How does this happen? So how does this process occur, or how is this association made? A drug in plasma and drug in tissue exists at an equilibrium, means that they exist at a balance between these two compartments. But the one that is exposed to metabolism and excretion is the drug in the plasma. So as the drug is metabolized, its level in the plasma will drop, and the drug that has been distributed in the tissue just now will re-enter the circulation to ensure that the levels in the both compartments still exist at an equilibrium. So as you can see, if the VD is higher, means that there are now more drugs in the tissue. This process will happen, this equilibrium process will happen back and forth for a prolonged time, thus contributing towards a longer or bigger half-life. So now I reiterate again that drugs with high VD means there is less drug in the plasma to be metabolized and excreted. So there will be a low excretion rate even with that. Couple it with the fact that drugs with high VD, there will be more drug in the tissue to re-enter the plasma as the levels of the drug in the plasma drop. So this contributes towards the storage form of the drug in the tissues. So you'll see this storage referred to as being a drug reservoir in the textbooks. So combined both facts, and you have a longer half-life for a drug with a high VD compared to a drug with a low VD. Okay, from the max plasma concentration, the rate of excretion in general is usually exponential. Even though I've said before that the graph, the curve drops at a linear rate in the beginning, but throughout the whole process of excretion, the rate of excretion is exponential. So as the plasma concentration drops, it takes longer and longer for it to reach a zero. The measure of the rate of excretion is by a measure called clearance. Now, the definition of clearance, especially if you read in the books, can be quite confusing, but I'll try to make it simplified for you. The volume of plasma cleared, or I would prefer the terminology clean of drug in a defined period of time. So the unit is amount per hour or volume per hour, and this is not a measure of the drug, but rather than the amount of the blood that is cleared of the drug over a certain period of time. Okay, let's see whether I can make it easier for you to understand about plasma clearance. So imagine that this is the human body with 5 liter of plasma or blood, and inside of this 5 liter there is 100 milligrams of drug, which exists at a concentration of 20 milligrams per liter. The excretion rate is about 10% of the amount of drug per hour. So 10% times 100 milligrams is about 10 milligram of drug being excreted per hour. So at the drug concentration of 20 milligrams per liter, 10 milligram constitutes about 0.5 liter of plasma volume, or is actually contained within 0.5 liter of plasma volume, 500 mils. Okay, so if you use this formula, and we can determine that in the 1 hour that it takes to eliminate 10 milligrams of drug from the body, a hypothetical 500 mils or 0.5 liter of plasma is actually cleared of drug in 1 hour. So that is what is contained in the beaker here, about 0.5 liters of plasma. So the plasma in the big container still contains the drug, whereas the plasma in the smaller beaker here, 0.5 liters of it, has been cleaned from the drug, and which is what plasma clearance is all about. I know it's a bit confusing, but you'll see in the subsequent slides the need for us to talk about plasma clearance. Okay, plasma clearance. It is a reflection of the body's ability to eliminate drug, and in practice is actually measured using the unit milliliter per kilogram per minute. So it is still a measure of how much of the blood is cleared of the drug in a specific amount of time. Why is this significant? In clinical practice, this plasma clearance is used to determine the dosing rate or the dosing frequency of a drug in order to achieve a certain plasma concentration, to of course produce a certain pharmacological effect. So the formula here is the dosing rate or frequency equals to CL, which is clearance, times CSS. Okay, what is CSS? CSS stands for steady state concentration of the drug. This is a new terminology which I will be explaining in the next few slides. So one final thing about plasma clearance. What is the implication of a reduced clearance to the half-life of a drug? Think about it for a minute. Okay, now if you think about it, if there is reduced clearance, this indicate that there is reduced ability of body to eliminate the drug. Therefore, the slope of the curve of our plasma concentration versus time curve will not drop at a faster rate, or it will be more prolonged. So because of this, a reduced plasma clearance is usually associated with a more prolonged half-life. Okay, I'd like to take a few of the final slides here to talk about steady state concentration. This plasma concentration versus time curve is a curve that is produced for a single dose or single administration of a drug. What will happen to the curve if another dose is given at the time of half-life here? So let's see. As you can see here, this is the original plasma concentration versus time curve. So the dotted line here indicates the half-life. So if we give another dose here, there will be a similar curve, but now with a baseline at a new baseline, and will produce a higher max plasma concentration, but eventually it will still drop off. And if we give another dose here, the process will continue on and on and on until a steady plasma concentration is achieved, which is depicted by this figure here, which I've taken from Goodman and Gilman's. So if you can see here, the steady state is obtained after about 4 half-life, and the time to reach the steady state is independent of dosage, because as you increase the dosage, the half-life still is constant. Okay, the steady state is obtained indicates that the rate of absorption and the rate of excretion is now similar. So this smaller CSS here is depicting the blue line, which is the calculated average steady state concentration. So the average is obtained by averaging, or by taking the peak and the trough levels of the plasma concentration versus time curve. Okay, don't worry too much about steady state concentration at this point for this lecture, as I will go into much more detail about steady state concentration in the next lecture. The average steady state concentration can be determined or controlled by the doctor, and this has implications when we start talking about loading dose and maintenance dose in the next lecture. So in summary of this very short lecture, time versus concentration curve is used to calculate bioavailability. VD will determine tissue penetration of drugs. Clearance reflects the rate of drug elimination, and both VD and clearance will directly affect half-life. So I'd like for you to revisit the objectives for this lecture and look at the areas that you are not clear about and view the video again. Some details might be omitted from this lecture, and that is the the onus is now on you to go and have a look in the textbooks and find out the details that might be missing from this video. So I'll see you in the next one. Happy studying.